All right, so last time we went through some of the basics of how you would implement some computational geometry algorithms on a computer. And most of these algorithms that we're going to see in this course, at least, will basically boil down to orientation tests of some form or another. And orientation tests are examples of rational functions, which means that we can calculate them exactly using extended arithmetic or other various tricks. And we saw a couple of different ways to do that. But today, I'm going to spend a little more time talking about orientation specifically and go into some more detail about how this would work. And we're going to see another kind of geometry. So previously, we've seen affine geometry. This is usually written the blackboard, A to the D. And it's an example of what we would call a flat geometry, which basically means it has zero curvature. This is kind of the standard geometry you see in most textbooks or places. The other kind of geometry we also saw was projective geometry, which turns out to be way simpler than affine geometry for calculating or representing things. And projective geometry is not flat. It's actually curved. So it's a form of hyperbolic geometry, which means it has less than zero curvature. And in these geometries, affine space has the property that parallel lines don't intersect. And in projective geometry, every distinct pair of lines intersects in one unique point. So projective geometry simplifies a lot of things because transformations just become matrices and linear operations, and it's much easier to describe things like flats or lines or planes in projective space. But the problem with projective geometry is that it is not possible to define a half space, for example. So if we think about what's going on in the projective plane, if we imagine that we have, say, a sphere, right, then in projective geometry, the opposite points on this sphere are identified. So this point here is the same as this point here. So if I create like a plane, for example, then all of the points on this half of the sphere have to be identified, and same with all the points over here. So the half space you see doesn't actually cut the space in two. And so one problem with projective geometry is that it's an example of a non-orientable space, which means that you can't consistently assign an orientation to any tuple of points. Another way to think about this more algebraically is that in projective geometry, if I have a point px, py, pw, then this is going to be similar to any point kpx, kpy, kpw for any choice of k. And what this means is that if I have a determinant, for example, something like px, py, pw, qx, qy, qw, and rx, ry, rw, then I could rescale any of these columns by a factor of whatever number I would like. And if I rescale it by a negative value, then that's going to change the sign of the determinant. And so the orientation test won't be well defined in projective space. And so this is a problem. So today we're going to talk about the last kind of weird and crazy geometry that we'll see in this course, and it's the one that we're going to continue working in going forward. And it's a very simple modification of projective geometry, but it has some interesting consequences. And so this geometry is called oriented projective geometry. And we're going to write it using t to the d. And this turns out to be an example of an elliptic or spherical geometry. And it has a positive curvature. And one consequence is that every distinct pair of lines will intersect in 2 points. So that's the weird way to think about it. But we can unpack this a little bit. And so if we replace lines with oriented lines, then the oriented lines will intersect in 1 point. Right? So what does it mean to have an oriented line or an oriented point or an oriented space? Well, orientation in geometry is basically the same as this concept between left versus right. And so in some sense, there is no absolute definition for an orientation of a space. You can only define it relatively. So in much the same way that you could take all of regular space and you could replace every occurrence of the word left with the word right, just swapping them all around. And while you might become confused or dyslexic, there would be no real change in the way everything would work. You would just swap one word with the other, and life would go on. Nothing would be any different. And so the only way in which we can define something like left or right is by making an appeal to some other space or some fixed frame of reference within the space. And then from that frame of reference, we can say whether or not another frame of reference is oriented in the same way as that frame of reference, or if it's been reversed or reflected in some way. Concretely, what does this mean? We can say that a map, right? So here's the concept of an orientation-preserving map. Or more precisely, we'll say a linear invertible function preserves I should actually say a linear invertible function. So if it's invertible, we're going to require that it goes from the same space into itself, right? Orientation if and only if its determinant, call it m, is greater than 0. So this is the basic idea, is that we're going to use the concept of a determinant, which is itself something that's dependent upon our choice of basis within the space. And we're going to say that if this function m preserves that orientation of the basis, right? In other words, if the determinant is greater than 0, then this function preserves orientation. And if it has a determinant less than 0, then we'll say that this map is an inversion or a reflection. We can come up with different words to describe it, but that will basically flip the orientation of the space around. So that's the basic idea, right? And so in oriented projective geometry, we're going to look at something like a restriction of projective geometry, where all of our transformations preserve orientation. So they're just a special subset of projective transformations that happen to keep the sign of your coordinate system fixed. So this is sort of like we're looking at only the transformations which preserve the right-hand rule in physics, if you think of it in that sense. So, okay. Now let's get a little more concrete about this. So what does oriented projective space look like? What are the points inside it? And how do we represent things like lines and oriented flats? And the story is pretty similar to projective geometry, as I sketched out earlier. So this is oriented projective space, t to the d. And similar to projective geometry, it's going to look like a d plus 1 dimensional real space. But instead of modding out by all real transformations, we're going to only mod out by the positive transformations. So these are basically non-zero rescalings of points. in other words, we have the following symmetry for congruence. Right? So we'll say the 2 points are equal in oriented projective space. If wx, y will be proportional to kw, kx, ky, if and only if k is a positive real number. So this means that instead of being points generated by lines, they're now points generated by rays. So there's a couple of different ways we could visualize what this space looks like, in the same way that there are multiple ways to think about projective space. So if we start from this picture of a sphere, so we'll imagine that here again, this will be our xy plane, and then up is w. If I take a point here, and I look at this ray, right? So this can be the point p equals, w x y, right? So this whole space of points, or this whole ball, is what our oriented projective space will be. And so all of our arithmetic and operations will, basically transform points on this sphere to other points on the sphere. And flats will basically look like intersections of, half spaces or lines and planes with this sphere. So for example, a line in projective geometry will look like a circle in some sense. So if you take like a pair of points here, call this A, B, then this would be the join of A and B. All right. So we're all good on this so far. Simple enough, right? So that's kind of the abstract model. So how do we interpret this then as being sort of a geometry of points in a plane? Well, the idea is that we're going to select some circle to represent the Tn-1 at infinity and cut the sphere into 2 pieces. So this is sort of the spherical model, and hence why this is an example of a spherical geometry. The other sort of model that we can have, though, is something more akin to the w equals 1 plane that we drew for projective geometry, where what we're going to do is put a plane up here. And this will be we'll start with a coordinate system here. Again, so we'll have x, w. And this will be the plane w equals 1. And this is going to be the top half of the sphere. So we're going to think of the whole top plane as mapping up here. There's going to be another plane, though, for the bottom half of the sphere. And this is w equals -1. And this is going to be the bottom half of the sphere. And then for the equator here, we're going to just have this circle, which is w equals 0. So this is where the center line goes. So the interpretation of this is that in oriented projective geometry, every one of our points is going to have equipped with it some sort of orientation or charge. And so the points that live on this top plane, we're going to call them positive points. And the points that live on the bottom plane, we're going to call them negative points. And then the points here, these are just points at infinity. So the idea is that this is our positive points. We'll just use black. These are negative, and then these are infinity. So this also gives us a couple of different ways that we can think about Tn topologically. So from this sort of picture, right, we can conclude that, first of all, this thing is homeomorphic to the surface of a D sphere. Right? So if we basically think of the geometry itself at a topological level, it's just the surface of a D-dimensional sphere. But another way that we could also think about it is that it's two copies of affine space glued together, plus a lower dimensional copy of T. Or yet another way that we can think about this is that it's two copies of projective space glued together. Because if you think about projective space, it's basically half of a sphere, because we're identifying each of the antipodal points in projective geometry. And in oriented projective geometry, we remove that identification. So now we're just left with a sphere. So these are sort of a couple of different ways that we could think about the geometry of projectives, or of oriented projective space. And in practice, this picture turns out to be the most useful, where we're going to think of it as just being two copies of affine space. So there's another way we could draw this too, right? Or another type of picture, which is that we can just smash these planes together, right? And then just draw it flat on the blackboard. So in this way, this is sort of the smashed, I don't know, it's not a technical term, but we can imagine is we're going to have our points, A, B, C, and then each of these points is going to have some orientation assigned to it. And for the points at infinity, these just look like pure vectors. So this could be like maybe a direction D at infinity. So we'll see why in a moment this makes sense to think of these points at infinity as just being pure vectors. But the sort of sneak preview is that you can imagine if you wanted to add one of these points working just in the ambient space to another point, then what you'll end up with is a ray, in a sense, shooting out to infinity along that direction. OK. So that's the basic story for points. What about flats? So points are just the start of everything, right? We would also like to deal with higher dimensional subspaces in oriented projective space. And we would like to basically define them using a similar type of relation as we did up here. So we're going to say, when are two flats going to be congruent or isomorphic to one another? So we'll start out by giving a description of the flats in terms of coordinates, which, as we know, can be done using just matrices, right? And then using that description, we will say when two matrices represent the same projective flat. OK. So here's the concept. So flats. We'll start with the primal version. So the primal version is basically given a map, some matrix M, from, say, Rn to Rd plus 1, just in terms of the coordinates of this space. So we're going to create a rank n flat, basically. The flat is essentially represented by the image of this matrix. But when we think about the image of one of these matrices, it generates a whole subspace. So we want to also keep track of the orientation of that subspace in some way. And so the way that we're going to do this is we're going to say that two flats are congruent if they are related by some linear transformation that preserves orientation between the two. So in other words, suppose M is a column matrix, right? So we'll say it's generated by Px, Py, Pw, Qx, Qy, Qw. Then we're going to say that the image of this flat will be similar to some other flat, Px, Qy, or Qx, right? Py, Qy, Pw, Qw, times some matrix which we'll call R, for the determinant of R greater than 0. So this is the idea, is that R is going to be basically a 2 by 2 matrix. So R will be a map from Rn to Rn. So the idea is that if we start from Rn and we apply some orientation-preserving change of variables to Rn, then we'll say that the resulting image of this is still going to represent the same flat. So the idea is that we're taking the orientation of Rn in its standard basis here and we're moving that over into this space when we transform it over there. So how can we sort of visualize what's going on here? Well, there are a number of different sorts of pictures you can draw. One picture that works in a plane pretty well is if you imagine if you have like a line in 2D, then we can imagine that we're just going to designate some half of this line or some particular direction pointing along this to be the orientation. And so this could be, say, like, L. And then for this same line, there would be maybe an oppositely oriented line pointing in the other direction, which is the negative version of that same line. And so this actually becomes pretty useful, right? Because now we can talk about the orientation of things like half spaces in this model. Whereas in the case of a projective model, we were just stuck with a half space, or like a plane. And with that plane, it's not clear which half of projective space it's picking out, one way or the other. So, okay. So that's how this works for primal vectors. And the story for dual vectors is pretty much the same. The only thing that really changes is that instead of multiplying on the right, we have to multiply on the left. So I'll just erase a couple of things here. So in this one, the direction of this map has to go the other way because basically it's generated by the kernel of this. And our matrix is now going to be a transpose. Say this thing is similar now to R times the original matrix. For the determinant All right, so that's the idea. So in this way, we can now define oriented flats, right? And we can use the same notation as before, where if you recall, the square brackets means that we're going to concatenate along columns, and the angle brackets means that we're going to concatenate along rows. All right, so that's flats in a nutshell. I'll draw a couple more pictures of ways to visualize this. So for lines, it's straightforward. In 3D, in addition to lines, we also have planes. And so I'll just draw a couple of pictures of oriented flats. So here are some 3D pictures, which may be helpful. So if you have like a plane in 3D, we can think of this as basically being a plane with some normal direction associated to it. So plane, an oriented plane, could look like that. For an oriented line, we'd want to think maybe of having some sort of handedness or spin along the line. So this would be an oriented line. And then for points, again, we'll just write them as, say, plus or minus. So these are just some sort of graphical notations for how we'll denote the orientation of different subspaces. OK. So, so good so far. All right, so a couple of things have to change also with the way we calculate meet and join of flats. All right, so if we, all right, so let's suppose we have a flat, represented by a pair of vectors PQ, right? Suppose then that we change the order of the two columns, P and Q. So what happens if we swap them? Well, if we look here, this matrix is going to just be the PX. We'll start from actually this matrix here. This matrix here is going to be QX, QY, QW times PX, PY, PW. And the left-hand side is going to be equal to this thing times a permutation matrix, which just swaps the two rows around. So this thing here is just PX, PY, PW, QX, QY, QW. So what's the determinant of this matrix, right? Well, we can calculate that directly, right? So it's AD, well, that's 0, minus B times C. So the determinant of this thing is -1. So these two are not equal. Instead, this thing has to equal negative this thing, right, in order for this to be correct. And this extends more generally to the definition of meet and join, which, as we recall in the dual and primal forms, respectively, consist of just concatenating two sequences of columns or vectors. And so in oriented projective space, meet and join are now examples of anti-symmetric operators, right? They no longer commute, but they now anti-commute. So the conclusion of this is that this is equal to there, so that if we take the join of P and Q, this is equal to -Q join P, right? And similarly for the dual story, we have that P bracket Q is equal to -Q P, or in other words, if we take Q meet P, this is equal to -P meet Q, however we want to define it. All right. So this is for PQ points. And I should actually phrase here that this should actually be for PQ lines, right? Because we have to work in this other thing. So maybe I'll just write it like this. I'll just put a star here. Right, now I don't need to make that extra constraint. All right, so that's the basic thing that happens when we change meet and join for points. Now, what happens if we have higher dimensional flats? Well, we have to remember that every time we flip one of the two sequences here, we have to interchange with all of the other elements in a sequence. So if we do this, then for every element in the first term over here of P and Q, we have to go move it past as many elements in the second vector. So to kind of draw it out, we start out with, say, so this is just maybe a little bit of algebra here. So we start with A0, A1, etc. Then we have our B0, B1. We want to move all of the A's over here. Then this A has to basically, the last A has to move past all of the B's, then the next A has to move past all the B's, and the next A has to move past all the B's. And every time we swap one of them, the sign changes. So this means that in general, the total number of swaps is equal to the number of B's here times the number of A's. And the number of B's is the rank of this flat, and the number of A's is the rank of this flat. So if we do that in this sense, right, we arrive at this somewhat famous result, that if you take two flats, S and T, and you exchange their order in oriented geometry, then this becomes the rank of S times the rank of T times T join S. And the story is almost the same over here, except remember we're working with these square brackets, and so it's no longer the ranks that have to change, but they're co-ranks. And remember, the co-rank is just d plus 1 minus the rank. So this just becomes sin t is equal to -1 times co-rank s times co-rank t s meet t. Okay. So that's all so far straightforward, probably. And duality behaves pretty much the same as before, right? Just sending everything to its transpose. And so we don't have to worry as much about that interacting with orientation in any kind of weird or unintuitive ways. OK. So this is all good so far, because I'm going to erase this now. Is that OK? All right. So, all right. Now, what about this?
Sorry, you have S join T and then S join T on both, or S and T on both sides.
Oh, it should be T and S. Right. Yeah, that's the idea. I mean, basically, we're just talking about what happens if you flip them, and how the sign changes or the orientation flips. So, OK. So now one of the main algorithmic things that we care about with orientation is calculating the orientation of a tuple of points, or more generally, some collection of flats. So the way to make sense of this formally, right, in terms of oriented projective geometry, is that we're going to imagine that we have a pair of flats where we're going to say, given a flat S and another flat T, where the rank of S is equal to the co-rank of T, then suppose S is basically determined by the image of some matrix M, and T is equal to the kernel of some matrix N. Then we're going to define this operator called the relative orientation of T, which is the sign of the determinant of N times M. Right? So that's the idea. So we're just going to take the map from S and then push it all the way through the map to T. So in the case where, say, like S was a point and then T was a half space, all that we're doing is basically dot producting the point with the half space. And in other contexts, it becomes some different sort of operation. So that's the basic formula here for calculating orientation. And you can see that the special case where we have a tuple of points, or d plus 1 points, this would be the case where we'd have like maybe a plane and then the last point. And then we can imagine that we're just testing the point against the half space determined by the previous d points. So that's the basic geometric operation that you really need to calculate in most computational geometry algorithms. So all right, this is kind of neat, and it simplifies a couple of things. But where oriented projective geometry really becomes useful is when we start dealing with polytopes. So far we've dealt with flats, and we now have these extra oriented flats, which are kind of nice. But the neat thing is that now with a flat, say a co-rank 1 flat or a rank D flat, so basically like a plane, we can determine a hyperplane. So from delta, given a rank D flat, i.e. a hyperplane, we'll call it S, or let's call it H for half space. H partitions TD into 3 parts. So we have basically the collection of all points P. You have the set of all P delta H greater than 0. We have the P H equals 0. And then the P diamond H less than 0. OK? So similar kind of story, right? And what we'll do, so we'll call this set the set of all points P less than or equal. All right, we'll go with greater than or equal to. I think that's what I was. No, less than, right? Less than or equal to 0. The negative half space H, and then these ones P diamond H greater than or equal to 0. So this is sort of the closure of the negative set. Unless otherwise specified, we'll assume that a half space is of this form. Right? And it doesn't matter. We don't really need to support both types of half spaces because we can always flip the orientation of H and then get the other half space. Right? So whenever we say something is a half space, we're basically talking about this set. So it's the set of all these points which have a less than or equal to 0 dot product with that half plane. OK, great. So that's the concept of a half space. And with half spaces, we could, again, form a notion of convex polytopes by intersecting them together. Right? So again, we have an idea called an H polytope. So H polytope just says, given a set of half spaces, H polytope is some set P, which is equal to just the intersection of all of these HIs. Right? And this is already a pretty neat thing because we couldn't, work in sort of homogeneous coordinates with these polytopes in affine space. We have to do this, in oriented projective space because otherwise this half space thing wouldn't even be well defined. So that's well and good. So what does a V polytope look like in oriented space? So this becomes a little bit trickier because we have to define what a convex combination would mean in oriented projective space. And the naive definition of just linearly interpolating the points as we did in affine space doesn't quite work. So we're going to move to a slightly more general notion of a convex combination, which is called a conical combination, or a notion called a cone. So, all right, I'm going to need more space here, so I'm going to erase a bunch of stuff. So H polytopes, pretty much the same deal. But V polytopes become much more interesting, and actually a lot nicer than they were in affine space. So here's the idea. All right. So given a set, so some finite set V sub I contained in TD, define the cone of V to be the set of all combinations plus an minus 1 V, an minus 1 V n minus 1, such that each ai is greater than or equal to 0. And that's it. Right? This is pretty much the same thing as a convex combination, except we just removed the constraint that they all have to sum to 1. All right? So this is a cone. And I claim that this is actually the more natural definition for a convex polytope in projective space. So here is a picture of what this looks like. So I'll draw it in the spherical version first. So here is T2. So what this cone is we'll basically pick a set of vectors here on the surface of the sphere. And then the cone spanned by these points is just this region going off to infinity here of all vectors that we can write as positive combinations of these points. So we'll call this, let's label them, we'll call this A, B, C. And then this whole set here is the cone of A, B, C. All right. So this works fine for points which happen to be living in the positive side of the sphere. But what about points at infinity? Well, in oriented projective space, it's totally OK to take a cone combination of a point in the plane here and a point at infinity. In fact, we can even draw what this would look like. So imagine I take a point here and say a point at infinity. Well, the cone spanned by these two things is just going to be this fan. And then the intersection of the cone with the sphere, which is basically the set generated by this point, is just going to look like this ray that goes off to infinity. So in this way, we can actually represent rays and unbounded polytopes as V polytopes. And this is crucial, because without the ability to represent unbounded V polytopes, we don't have any way to talk about the dual of a V polytope as being an H polytope, or the dual of an H polytope as being a V polytope. Because if you recall, in affine space, we could have unbounded H polytopes, but we could not have unbounded V polytopes. Here, unbounded V polytopes are totally OK, right? No big deal. We just take cone combinations, including points at infinity, and it all works. And you just write the code just normally. It's just the same old basic stuff, really, really simple. So to illustrate, for example, for this line, right, if I draw a picture of what's going on in the plane, I can have some base point, call it P. We'll have some point at infinity, which will be a direction vector, D. And if I take this cone combination of P and D, I'm just going to get this line going off to infinity. So this will be the cone of P and D. All right, so now we can do all of the sorts of sets that we would be interested in.
Sorry, what's this picture of the P and D?
So think of P as being, this is imagine that we're in the top half. So we're basically going to think of this as basically the flat 2D picture of T2, right? So imagine P is a point and then D is a point at infinity, which means that we're going to think of it as just being like for each point at infinity, it's going to live on this circle somewhere here. So each point at infinity has a direction associated to it, but it doesn't have any particular point on the surface of the sphere. So if we take one of those points at infinity, and then we combine it with the point P, we're going to get a ray that goes all the way off to infinity, right? And what's going on here is we actually have the cone of this point at infinity plus this point on the top of the sphere, and it just sweeps out this cone arc here, and that forms the ray, right? So hopefully that's clear. Right. So, OK, this leads us to the definition of a V polytope, which is as before, except replace convex combination with a cone. So a V polytope in Tn is just the cone of a finite set. That's it. There's nothing else to it. OK. And crucially, V polytopes don't have to be bounded, right? Or actually, another way to think about this is that if you actually look at them in the space of a sphere, H polytopes in oriented projective space are all bounded. So everything is bounded in some sense, right? But if you look at the sort of image of a V polytope, it doesn't have to be bounded down here. All right. And so here is kind of the fundamental theorem of polytopes in projective space, which is not true in general space. But it is that every V polytope is an H polytope, and every H polytope is a V polytope. And I'll write that down here. And this is called the, I think it's Minkowski whale, right? Something with Minkowski. Everything involving polytopes has Minkowski on it. So this is the Minkowski whale theorem. We'll just say it like this. Every V polytope is an H polytope. And vice versa. All right? And we already proved that H polytopes become V polytopes using Fourier-Motzkin elimination. And using the next thing, which I'm going to show you, we can actually prove the opposite direction really, really easily by just repurposing that same proof. And the thing that I'm going to show you next is the concept of duality, or sometimes called a polar cone for a cone. Right? Or if you know something about linear algebra and convex optimization, it's exactly the same concept. And it's exactly the same concept also as the dual of a flat. So, okay. This is in some sense like the fundamental theorem of polytopes, right? So, what do we have to say about duality? Well, okay. To explain how this works, it'll be useful to introduce a kind of matrix notation for writing a polytope. So if we have an H polytope, right, so I'll say an H polytope written as basically the intersection of all these HIs in some big H. Define this matrix, which we're going to call A, to be just a matrix whose rows are each of these HIs. So I think we're requiring these guys to be sort of represented by column vectors, right? So we'll just think of this as like H1 transpose, etc., to Hn minus 1 transpose. Right? So each of these H's is one of these supporting hyperplanes of this polytope, or they're one of the facets, is another way to think about it. So let's call this guy P. So we're going to say another way that we could write P, and it's just a simple notational thing, is it's the collection of all x, such that when we take A and apply it to x, we get something which is, did I use greater than or equal to or less than or equal to? I changed this at the last minute. Such that it's less than or equal to 0. That's right. OK. So, all right. This is another sort of notational form. Or we can alternatively think of this polytope as defined by the system of linear inequalities, x less than or equal to 0. So this is sort of the matrix formula for writing an H polytope. Or another way to think about this is that we can also define a V polytope in this way. So V polytope. And we'll write this as basically the dual of this H polytope, which is that if we took this matrix A and we transposed it so that now each of these H's, instead of being half planes, are now all oriented points, then this dual polytope of A is going to be the dual of P star is the V polytope formed by the cone of all of these HI stars. Or another way we could write this formally is that P star is equal to the set of all points of the form A transpose Y, right? Because we're just flipping that matrix. And then we're going to define Y to be such that there exists a Y in Rn. Right? So we're just going to think of Y as a set of weights that we're going to multiply each of these points by, where each component of y is greater than or equal to 0. Or if we write it as a system of equations, this is something of the form A transpose y equals some vector x, right, where y is greater than or equal to 0. So these two forms, or these two systems of linear inequalities, are precisely dual to each other in the same sense that their polytopes are dual to one another. All right? So this is, in a sense, how polytope duality is defined, right? Another example of this is if you actually look at a linear program. These are actually dual linear programs, right? And we'll frequently use that concept to formulate a number of interesting geometric problems. In fact, the most interesting things you want to calculate about polytopes turn into instances of linear programming, right? But I think I'm getting a bit ahead of myself saying that. Right. So a couple of notes on how duality for polytopes changes a few things. So I'm going to erase stuff and free up some space here. So we can start a similar sort of table. And we'll expand this and add more sorts of operations as we go on. But the main point of duality is that you can basically take any expression of regular H polytopes and convert them into an expression of their corresponding dual V polytopes, and everything just turns into exactly the same algebra, right? Because all that's going on is you're just transposing every matrix and vector in your entire equation. So, OK. Yeah, there was something else I wanted to say. Oh, right, I erased the Brun-Minkowski thing. OK. So here's the easy way to kind of get to the proof of the Brun-Minkowski theorem, is that given this duality, what we can basically do is first apply a dual to our H polytope that we want to show as a V polytope. And so now we'll get a corresponding V polytope, show that that is equivalent to an H polytope, then apply the dual again, and now we're done. And because this duality operation is an involution, this resulting V polytope that we get is going to be the vertex set of the H polytope that we started with. And so in this way, you can take any convex hull algorithm and turn it into an algorithm for vertex enumeration. So all you do is you start from your convex hull set, or your set of half spaces you want to compute the vertices for, take their dual, compute the convex hull, take the dual of that, and now you have the vertices of your final polytope, right? So in this way, enumerating facets and enumerating vertices are just duals of the same problem. So we have basically two algorithms in one. And this is like the main motivation for introducing duality, is that we effectively get twice as many algorithms as we would have started with. And sometimes, problems can be much easier to solve in one way or another, or converting from one representation to a different one. So, right. OK. Operations with dual polytopes. So here's sort of a quick table of duality for polytopes. So again, if we take a V polytope, and we take its dual, we get an H polytope. And if we take an intersection of two polytopes, so we take like, A intersect B, then this becomes the cone of their union. So this becomes A star union B star. So in this sense, the cone is dual to intersection, which makes sense because what's going on here is you're just, in the case of an H polytope, concatenating rows. And in the case of a V polytope, you're just concatenating columns. All right. Here, if we have an oriented point, it becomes a half space, right? And a number of algorithms will basically translate from one representation to the other. So for example, we're going to call this point membership, which is test if a point is contained inside a polytope or not. We'll turn into the problem of half space containment. So test another way to say this is we'll just say x in P, and then this will basically say P contained in X star, the dual half space, right? So those two problems are, dual to one another. Right. I brought a computer down here so I could show you a couple of pictures. Oh, I didn't even record this thing. Oh my God. It says battery level too low. Or whatever. Okay, I'm just going to take this off. Sorry for the people who weren't here. Okay, false alarm. It's just complaining about the battery level on the microphone. It's actually recording. All right. Okay, so all right. So can you guys see this? Or it looks like it just has to take a moment to kind of warm up. Okay. All right. Okay, so here are some random pictures of polytopes in 3D. And the basic, to get kind of a geometric feel for what duality does, is that it's going to swap faces with vertices. So for every vertex of this polytope, we're going to get a face, and for every face, we're going to get a vertex. So if I calculate the dual of this thing, by typing in this, we get some weird looking polyhedron. I can do this with other polytopes. So I can take an icosahedron, and the dual of the icosahedron is a dodecahedron. Similarly, if I take a cube here, I take the dual, then I get an octahedron. All right. So remember, what's basically going on is that the faces of this cube are becoming vertices of the dodecahedron, and vice versa. So hopefully this is clear. And then also for things like a tetrahedron, if I start from one of these, then the dual of the tetrahedron is just a tetrahedron, which is pretty boring, right? Because the tetrahedron is an example of a self-dual polytope. Right. Okay, so that's sort of like the basic graphical interlude. I'm going to turn off the power, and then turn the lights back on. Right. Okay, so that's duality for polytopes. Yeah, so I have about 15 minutes left. I wanted to go over a couple of things on the homework really quick. And then, I don't know, or I can do a couple more examples of some things or talk about some other problems. So which would you guys all prefer?
Homework.
All right. So we'll do this really quick. So there was one thing a lot of people got wrong on the homework, which I did explain earlier, but I will explain it again, because it is a subtle point. And the basic problem is that flats transform differently than, or dual flats transform differently than primal flats. All right, so that's the basic idea. So why does this happen? What's going on? Can we explain it? So we'll start with an example here. Right. So suppose we're just going to work in A2. All right, and suppose I have a line like this, L, which we're going to say is equal to the set of all points x, y, such that x equals negative y. All right, so this is just boring affine line, right? Or if we write this in the notation that we have from before, we'll think of this as just being the point 0, 1, negative 1.
We have w as the. Oh,
yeah, we're thinking this is w as the first component, and then x, y. So w, x, y, right? These are just this is our line, right? Now, suppose we want to translate it so that the origin moves to the point 1, 1, right? So let's say we want to do a translate. So 0 goes to 1, 1, right? Or the origin goes to 1, 1. So what would the matrix for this look like? So we'll call this matrix here T, right? It's going to be a 3 by 3 matrix. So anyone want to take a guess what happens, right? T should be a translation. So we're going to feed in, and it's going to have the property that if we feed in 0, 0, 1, it's going to spit out 1, 1, 0 or whatever, right? So any takers, right?
Well, it's just the identity, and then,
well, okay, like, yeah.
You can start with the identity and then change it.
Right. We'll start with an identity matrix. Okay. Yeah. And let's do, to make this sort of more consistent for people who are also taking graphics, we'll put W as the last component here. I don't know. It's just, I realize I'm just changing notation around a little bit, but this will be a little bit simpler for people who've seen them. So in computer graphics, if you have a matrix that's in, sort of rows by columns, like a right-handed coordinate system, where do you put the translation? Right? How do we modify this? Because we want to move 0, 0 to 1, 1. So if we should have the property that if we take t and we multiply it by this point 0, 0, 1, well, we'd like to maybe get out 1, 1, 1, right? Yeah, we'll just make these 1, 1, right? So that's right, okay, because basically if we plug in 0, 0, 1, rows by columns, we're going to get 1, 1 out. This is the correct matrix for T. All right. So now, suppose that we want to apply T to some flat. Right, we're going to go take T, and we're going to multiply it by a flat F. And suppose F is a primal flat, right? So that means that F is going to be T times the image of F, right? Another way to say this is suppose that F is equal to like the square brackets of P0, P1. Right? So if we do this, we're going to basically be taking T times the collection of all vectors x in Rn, because we're working in affine coordinates here, right? Where we're going to say there exists some, should actually be in Rd, there exists some y in Rn such that x is equal to f of y, right? This is the definition. So if we push this through here, right, then what we'll see is that basically this t will propagate through this whole thing. Or let's use the angle bracket notation. I think it'll be a little bit clearer here. So another way we could write this, which is equivalent, this is basically t times the collection of all points a0, p0 plus a1, p1 plus an minus 1, pn minus 1, right? For each of these ai's being some real coefficient, right? Because this is just the affine combination of all of the p's, right? So if I push it through, well, t commutes with the scalar multiplication in each of these cases, so I can just pull it onto the t. So this is straightforward, right? So in this one, I'm going to get a0 tp0 plus a1 tp1, etc., an minus 1 tp n minus 1. So I'll conclude that this is going to just be tp0, tp1, tp n minus 1. I think everyone got this right. So this was straightforward. That's clear, right? Now, the problem is that if you have something in the dual form, the story is not quite the same, right? And so here's what's different. So I'm just going to erase and make some space here. Right? And to kind of illustrate what's going on, so suppose we have our line here, L, right, which we already established was 0, 1, negative 1. So suppose we just applied this matrix T directly to the components of L. So we'll say that this is going to be that matrix 1, 0, 1, 0, 1, 1, 0, 0, 1 times, well, the W component has to go at the bottom, so that's 0, fine. And then we're going to have our x as 1 and y is negative 1. Right? Well, if we multiply all these through, what we're going to get is the line 1 here for the first component, negative 1 here for the second component, and then 0 for the third component, which is the line itself again. It doesn't look like it translated the line at all, right? Left it fixed. So what gives? What's going on here? Right? I mean, could it be that we use the wrong matrix? Well, no. We can test it by plugging in points, and it's fine if you plug in a primal vector. But the answer is that these dual vectors here have to transform using a different rule, right? And it comes from just the definition of the dual vector. So we'll do this really quick. So if I take t of, say, we'll just do it with like one component for now, right? But we could do this with multiple ones. It's the same story, right? This is basically t times the set of all points x such that v transpose x equals 0, right? That's the definition of this dual set, all right? So what does this mean? Well, I can pull the t in to the inside here, so it then becomes tx, right? Times v transpose x equals 0. Right? But this is t applied to x, not applied to v. Right? So I want to move the t in there, so I can basically use the fact that t is invertible to apply a change of coordinates and then replace this with a new variable. Let's do a substitution where we'll say u is equal to t inverse x in this equation. Then I'm going to get the collection of all u such that we have v transpose t inverse u, right? Equals 0. Actually, it should be tx. U equals tx, not u equals t inverse x. All right, so now I have v transpose t inverse u, but I still have this transpose here on this vector, right? So I want to basically apply I want to pull this thing in with t, so I'm going to use the additional fact that if I take AB quantity transpose, that becomes B transpose A transpose. And so when I pull it into all of this, I'm going to get U such that I have T inverse transpose times V quantity transpose U. And that is going to be equal to T inverse transpose V. All right? So to verify that this is in fact correct, I could calculate the inverse of this matrix. All I have to do is just make these -1, -1, and then transpose it and multiply it through. So what do I get if I do that? Hurrying a little bit here because I think I'm almost out of time. All right, if I do this, I'll get 1, 0, 0, 0, 1, 0, -1, -1, 1 times 1, -1, 0. Multiply this through, so I have a 1, again, -1, and I multiply through on the W component, and now I get a -1 times 1, so that's going to be -1. Let's see, so it's 1, -1, minus -1, Right. Did I do this right? Shit. I hope I didn't make a mistake here. Inverse transposed. Shit. Right. I don't know. I think I'm almost out of time. I think I maybe made a mistake calculating that. But it should be the inverse transpose, I believe. All right.
Calculate the inverse transpose of that matrix correctly?
I don't know. I think I did. Right. So this is a homework assignment, is actually figure out what's going wrong here because I'm actually out of time and there's a bunch of people in the hallway, I think, queuing up. So we're going to call it a day.
It's only 2:13, but I just got one out early.
Yeah.